Hi everybody, welcome to another video in Calculus 1, section 4.9, Antiderivatives. So in this section we will study about antiderivatives, which is opposite to, not opposite, it's the other way when we're doing derivative. So, a function capital F is an antiderivative of a function if f prime of x is little f of x for all x in the interval. So we will have a function and then a little function, little f. In that direction, if we take derivative, we have a big function into a little function, and then antiderivative is the other way around, almost. Right. Now there's a problem to this. The key word here is an antiderivative. Right. So, of course, when we go to some example, then we will see why it is the case. But the first thing we need to know is antiderivative is the opposite direction of the derivative when we do things. So, let's go to a theorem. Let f be an antiderivative of the function f. The key here, once again, is any. Then all the antiderivatives of the function f have the form f plus c, where c is arbitrary constant. Right. So we might have a function plus a constant, and then the thing is the constant derivative of constant is 0. So that's why we can add the constant to it, and derivative is still the same. So let's look at some example. Now, let's say if I have a function, let's say the x to the fourth, right? And then we take derivative of that is 4x cubed. Right? Now, derivative of x to the fourth is 4x cubed. Then we can say it f of x equal 4x cubed, x to the fourth, sorry, is an antiderivative of a function 4x cubed. Right. So x to the 4 is an antiderivative of 4x cubed. So because derivative of that is 4x cubed. So if we draw a diagram, x to the fourth derivative 4x cubed, and then antiderivative, of course, is the opposite direction, right? Now there's a problem to that. So of course that's easy to see when you draw like that. Now there is a problem to that. Now we have f of x equal x to the fourth, and derivative is that. Now, of course, go to another example. What if we have the function x to the fourth plus 2? Then what is the derivative? Derivative of this is also 4x cubed. Right? And then because of that, we can also say it f of x equal to x to the 4th plus 2 is also an antiderivative of the function for x cubed. So essentially we cannot add any constant with derivative is still 0. So that's why we say all the antiderivative will be the function plus a constant. So the constant could be anything, and then derivative still the same, because derivative of this constant is equal to 0. Right? So if we want to find all the antiderivative, we have to add to the constant to it, because all of this function x to the 4th plus any constant, derivative is still for x cubed. Right, so just add a constant to it when we find the antiderivative. Yeah. Right, let's look at some example. Right, find all antiderivative of the following function. Now we have to find all the antiderivative, meaning that we have to add a constant c to it. Now, so we have f of x is equal to 3x squared. So what is f of x? So that derivative of it is equal to 3x squared. Right? So we know the function is 3x squared. We need to find another function whose derivative is equal to 3x squared. Right? So we say what function will have derivative as 3x squared? And then you see x cubed, derivative of x cubed is 3x squared, right? So the derivative of x cubed is 3x squared, so we have to find, so the function is x cubed. Because the derivative of x cubed is 3x squared. But if we want to find all the antiderivative, we're going to add the constant to it. So this is an antiderivative of 3x squared. Don't worry, just like derivative, there will be some certain rules that we can use for each of them. Right, next. If the function is sine x, once again, we find all the antiderivative, so we will find a function whose derivative is equal to sine x. Right. And then we say so we know that derivative of sine is cosine, derivative of cosine is equal to sine, right? So let's just write in order to get to sine, we take derivative of cosine, because derivative of it will turn into a sine. However, derivative of cosine is equal to negative sine, right? So in that case, to guarantee to turn this to positive, we have negative cosine. We can turn that into a plus. Yeah. Since derivative of negative cosine equal to sine, we can say the function is equal to negative cosine of x. And if we want all the antiderivative of it, we will plus a constant c. Then derivative of negative cosine is negative sine, which is a sine. Derivative of constant c is 0. Right, so it's not that bad. Now 9x to the 10, we can write 9x to the negative 10. And then we write, right, what derivative will have x to the 10? X to negative 10. Right, so let's think. So let's write the question. We'll find a function whose derivative is 9x to the negative 10. Right, so what do we have to take derivative that has the x equal to negative 10? So in the rules of derivative, when we take derivative, we'll take out the power and the original power minus 1. So if we don't want that, we have to have the power. We wish one more. So when we take the power down, original power minus 1, right? Yeah, derivative of x to negative 9, we take the negative 9, original power minus 1, negative 9, minus 1, minus 10. So the reason we have minus 10, so that's why we start with minus 9. Just like last round, because that is minus, to ensure that it is positive, we turn the sign of both of them. Because that is the case, we can say f of x is equal to negative x to the 9, once again, plus the constant c. Of course, we can always verify by checking derivative of this. Derivative of this, negative 9, sorry. Derivative of this, of course, is going to give us 9x to negative 10. Of course, we can check that easily, right? Yeah. Derivative of negative x to negative 9 plus constant c. Negative, take down the negative 9, original power minus 1. Derivative of c is 0. Well, that gives us 9x to the negative 10. So, like I said, when we have the rules and we follow it, it will be a lot easier than kind of guessing here. Alright, now, before we actually have the rules, some basic rules, we should have some proper notation and proper terms for it. So, let f of x be a function, the family of all antiderivative. So, the family of all the functions that are antiderivative. So that is too long to say it. So I will put that together. Why do we define that to be something new? And that is, we define that to be indefinite integral. So indefinite integral is the family of all antiderivatives of the function. And the symbol of that is that elongated s and dx. So note that this simple elongated s and the dx goes together to signal the antiderivative of the function. The function we put in the middle, but that integral sign, that is the integral sign. The function in the middle is the integrand, and the x on the back will indicate what variable we're talking about. And those together is the notation, the elongated s and the dx. So those together is a notation. Just like when we write derivative, like x to the 9, for example, derivative, we do that for the derivative. Now, but if we want to write the antiderivative of it, then we have to have both the integral. So that is the indefinite integral, which is the family of all the antiderivative of it. For example, the last example, we can write indefinite integral of the function is equal to negative x to the negative 9 plus c. Right? Yeah, so that's the proper notation. And we say the indefinite integral of 9x to negative 10 is negative x to negative 9 plus c. Of course, we don't say the dx, we just say indefinite integral. Those together is the integral and dx. Later on, if it is clear to the context, we just say the integral of the function is equal to something. Right. Now, according to the previous theorem, if f of x is any antiderivative, then we can just add a constant to it to have the indefinite integral, which is the family of all the antiderivative, and the c here is called the constant of integration. Right. So we have the notation terminologies. Now we have the rules of integral. So the first rule, the power rule, just like when we have derivative. So the integral rule for x to the n, this is power rule, integral for x to the n. Unlike derivative, we take the power down and original power minus 1. So we take the power down and we multiply to it. So this instead, we will divide and we increase the power. So increase the power by 1 and divide by the same thing as the power. And notice that since we dividing, whatever we divide by, it cannot be 0. So in that case, n cannot be negative 1. And integral of a constant is equal to kx plus c. This is easy because derivative of kx plus c, derivative of c is a constant, 0. Derivative of x is 1. So that's why it's just k. Because antiderivative is the opposite direction. Antiderivative of k is kx plus c. Right, so that's it. And then finally, the properties, we can take the constant outside of the integral and we can split the integrals like that. Now, just go straight to some of the example that we have here. Remember, all we have here is the power rule, right? So first of all, we have to focus on just inside the integral sign and dx. Of course, the dx don't get that in the way because that's just part of the notation. The integral and the dx goes together, right? But since we use the power rule, it would be nice if we write everything as a power. So in that case, x, the power equivalent to square root is 1/2 power. Right. Now, I will apply the power rule to all of the powers. Notice when we apply the integral rule, the integral sign and the dx will not be there anymore. And I said the integral sign and the dx goes together. Those together is a notation. And then you say, why do we choose such a notation? Well, when we go to the next chapter, that explain why we use in those notation. But now the integral sign and dx goes together. One of them disappear, the other will disappear as well. And when they disappear is where we apply the power rule or any integral rule to it. Right. We have this power rule, right? The power rule says the power will increase by 1 and the power increase by 1 and then we divide by the same thing. That is the power rule. The integral of 2, well, integral of a constant, we will stick an x to it. And we say, what happened to the constant c? Well, get back to that in a minute. And x to the 1/2, just increase the power by 1 and divide by the same thing. Right? So that power rule, increase power by 1, divide by the same thing as the power. In that case, all the constant multiplier will stay there. The plus sign stayed here. -5 will stay there. Now, if we want to find all the antiderivative, we'll have the constant of integration. They will say, why don't we have the constant for each one of them? Well, of course, we certainly can have the constant for each one of them. Let me simplify this first. So that gives us 3 times x to the 6 divided by 6 plus 2x minus 5 times x to the 3 half over 3 half plus c. Well, let me simplify first and then we go back and say why do we have to have each constant. Right, now this we have 6 at the bottom, right? We can divide by reciprocal. Now notice the 6 is at the bottom. We can flip that. And then with the x to 6 we can just write like this. Plus 2x minus 5. The 3 half is at the bottom. We're going to flip, becomes 2/3. Right? And then x to the 3 half plus c. So that gives us 3 times 1 over 6 is 1 half. X to the 6 plus 2x minus 10 over 3 x to the 3 half plus c. So that's what we have. Right. And now get back to the question, why do we don't need to write separate constant? Right. Now let's just focus on that. I could write 3x to the 5 plus 1 plus a constant. Right. And then derivative of 2 is 2x plus another constant. So just make sure they're different. Constant 1, constant 2. And then 5 x to the 1 half plus 1, well, 1 half plus 1 plus c, another constant. Now we have a constant plus a constant plus another constant. We can add all of them together equal to just a constant. Right? So combine all the constant together is a constant. So when we integrate or we find the indefinite integrals, all of them, we can just combine all the constant into one. So that's why we apply the rules to all of the terms that have one constant at the end. That will be enough. And that's what we do. Right? Right, next. Up to this point, we only have one rule, that is the power rule. Right? The rule that can turn a function into an antiderivative. I mean, that is the only rule we have. These are the rules too, but the integral sign is still there. So we don't do any antiderivative or any indefinite integral here, because the notation still stays the same. When we apply the rule, the integral and the dx, both of them disappear. Right. Now, notice that we only have that rule, right? So we have to have the power of individual terms, so we need that first. So just like when we take derivative, we try to get that in terms of individual power terms, so we can apply the power rule. So we will split that into x to the 4th over x cubed. That gives us x to the first power. Yeah, just write x to the first power. Nothing wrong about that. And then x over x cubed. X to the first, by default, 1 minus 3 is minus 2, so minus 5x to minus 2. And then dx. Right. Now we can apply the power rule to this power and to that power of x. The integral of x, or x to the first, is increase the power by 1, divide by the same thing. The rule for that, increase the power by 1, divide by the same thing as the power. Right? any constant multiplier will stay. So that's just like what we did for the derivative, right? Just apply the rule, and this is the rule for the integral, right? When we apply the rule, integral sign and the x disappear, and don't forget there's a constant, right? When we get used to it, we can skip some of the intermediate step, but for now I will write everything. I have to give us x squared over 2 minus 5 x to the negative 1 over negative 1 plus a constant c. Now, divide by the number, meaning multiply reciprocal. Divide by 2, multiply by 1/2. Divide by negative 1, reciprocal. Yeah, this is still divide by negative 1 is the same as multiply by negative 1. I should put negative 1 here, but that's better. Right, we still have x to negative 1 plus a constant c, and 4 times 1/2 is 2. Of course, later on we just say 4 divided by 2 is 2, but yeah. I write all the steps here. Where the x. 2 x squared minus a negative, that's a plus 5 x to negative 1 plus c, right? So write everything as a power, individual power, and then we can integrate using power rule, which is each one of them. Right, now similarly we cannot deal with that, no product rule, no quotient rule, so we just have to multiply them out. That gives us 2z cubed minus 5z squared plus 2z and minus 5. Right? 2z cubed minus 5z squared plus 2z minus 5. Right. So we have individual powers. We can apply the power rule to it. So power rule for z cubed, z squared, z. By default, we can say this z to the first, and then of course the constant. Yeah, apply the power rule for each one of them. Since we apply the power rule, we integrate. We do not have the integral dx anymore. So again, z cubed, the power rule, increase the power by 1, divide by the same thing. Simple enough, right? Increase the power by 1, divide by the same thing. Increase the power by 1, divide by the same thing. And when there's a constant, we'll stick the variable to it. This case is z. Right, now there's a 2 multiplied to this, and then minus 5 multiplied to this, plus 2 multiplied to that, subtract, plus constant c. Right. Let's rewrite. 2 multiply z to the 4th over 4 minus 5 times z cubed over 3 plus 2 z squared over 2 minus 5z plus c. Right, now divide is multiply reciprocal. The 4th divide by 4 is multiplied by 1/4. Divide by 3 multiplied by 1/3. divided by 2 is multiplied by 1/2. And then 5z plus c. Okay. And then we write this. Of course, run out of space, but see. 2 times 1/4 is 1/2. Z to the 4th minus 5/3 z cubed. 2 and 1/2 cancel out. Z squared minus 5z. Let's see. Sorry, we don't have space at the end, but just simplify. 2 times 1/4 is 1/2. Z to the 4th minus 5/3 z cubed plus z squared minus 5z plus c. So that's what we have. Right. Now, so we have the power rule. Now let's go over a few other rules. First, let's review the derivative before we do the antiderivative or the indefinite integral. Derivative of sine is cosine. Derivative of tangent is secant squared. Derivative of secant is secant tangent. And then derivative of the cofunction to this is just going to be negative. Negative cosecant squared and negative cosecant cotangent. Right, so that is the derivative rule. The antiderivative, of course, is opposite direction to it. So since derivative of sine is cosine, so antiderivative of cosine is sine. Since derivative of cosine is negative sine, antiderivative of sine is going to be the negative. We can move to the other side. Tangent, derivative of tangent secant square, so integral of secant square is tangent. Derivative of cotangent is cosecant square. So if we want cosecant square, we have to take the negative to the other side. We have that. And similarly for derivative of secant is secant tangent. Antiderivative of secant tangent is secant. So the integral, the indefinite integral, is going to be secant plus c, right? So just opposite direction as the derivative. So those are the rules. Simple enough. So determine the following indefinite integrals of this function. So secant square, integral of secant square is going to be tangent. And just so we have all the antiderivatives, so we have the indefinite integral, the family of all antiderivatives, it's always plus a constant. So that's how we do. Right. Next. Next, we'll take the integral to the constant. That is the power rule. For x, we will stick an x to it. Integral of cosine. Integral of cosine is going to be sine. Right? So integral of cosine is sine. So integral of cosine, we're going to write sine. And there's a constant multiplier. To make sure we have all the antiderivative plus c. So this just equal to 2x plus 3 sine x plus c. Right. So simple enough. Now the next one is we have to do some trigonometry before we actually do it. So try to find the integral of 1 over 1 plus cosine x. So what we can do here is multiply by the conjugate. 1 minus cosine x. Let's see what happened. Right. So when we do that, we have 1 minus cosine on the top. Right. I'll just multiply out at the bottom. 1 times 1. 1 times cosine x, so negative cosine x, plus cosine x. Cosine x times cosine x, that's cosine square right. Now cosine cancel out. We will have 1 minus cosine of x over 1 minus cosine square. Right, now in trigonometry, every time we have sine square or cosine square, that is Pythagorean identity, namely sine square plus cosine square is equal to 1. Now if we subtract the cosine square on both sides, we have sine square equal to 1 minus cosine square. So this is what we have here. It's a sine square, right? That gives us a sine square. At the bottom. Right, now we can split. Because remember, in integral there's no product rule or quotient rule. We can just split and do term by terms. 1 over sine square we can split into separate integral if we want to, but I will not do that. I'll just say it. I will split like this. Now, 1 over sine is cosecant. 1 over sine square, cosecant square. Right? And this I can rewrite as cosine over sine times over sine, right? So cosine over 1 of the sine and then 1 over sine. Cosecant square and then cosine over sine is cotangent, and 1 over sine is cosecant. Now go back to the rule. Integral cosecant square is negative cotangent, and integral cotangent cosecant is negative cosecant. So we use those two rules. For cosecant square, that is negative cotangent, and cotangent cosecant is will give us negative cosecant. Right? Cosecant, integral cosecant square is negative cotangent. Integral cotangent cosecant is negative cosecant. Of course, we still have a negative here. So negative, negative, and negative. That's a plus. Before we do that, make sure there's a constant c. So this ends up being negative cotangent of x plus cosecant x plus c. Right. So we just have to follow the rules of the antiderivative, or I should say the integrals, which is all the antiderivatives. Right. More samples. Right. Now, integral of sine x, we know is cosine of x, but don't forget there is a negative, because the derivative of cosine is negative sine, is negative sign. So to negate that, we have to throw in negative. So that the derivative of negative cosine is equal to sine x. Of course, if we're not sure about it, always we can just take derivative of negative cosine, give us sine. Integral of cosecant square is negative cotangent. Yeah, so that is the antiderivative. We will multiply by 2 over pi, and it is not subtract, it is multiply 2. So just to be clear, we should put the parentheses around it, and this is multiply 2. Minus 2, and once again this is multiply 2. And then plus a constant c. So that gives us negative 2 over pi cosine of x minus a negative, that's plus 2 cotangent of x plus c. Right? Now, of course, we have derivative of that. We have antiderivative or the integral rules for that. Now, this we have a quotient, so no quotient rule, no product rule, remember. So what we can do is just have to split and try to simplify them into single terms. Now, just like the last example, first I brought a fourth in front. We have sine square at the bottom, so I will split that. Say sine times sine will give us sine square at the bottom. On the top, we only have one cosine, so the other one has to be 1. Sine square over sine square is 1. So that will give us 4 cosine over sine is cosecant. Cosine over sine is cotangent. And 1 over sine is cosecant plus 1. Now we apply the rules. Cotangent and cosecant is negative cosecant. Just like when we do the derivative, we have the table of all the derivative. We should have those formula with you. By the way, when we take the next test and the final, I will have the formula for all the antiderivatives. Of course, certainly we include this. So once again, we have cotangent and cosecant. That gives us negative cosecant. And there's a 4 in front of it, multiply to it. Integral of 1 of any constant, just multiply by the variable, and then plus the constant c. So we have negative 4 cosecant of x plus c. Right? So that is indefinite integral. Or if it is clear to the context, we just say it integral. Right. Now initial round problem. Initial round problem is a differential equation. So this is differential equation with initial condition is called the initial value problem. So we have two things, a differential equation and initial condition together give us initial value problem, which abbreviate IVP, initial value problem. Right. So a differential equation is the derivative, is the equation that has derivative in it, very much. And this is the most fundamental, the easiest possible of differential equation. We just have derivative equal to something. Now, if the derivative equal to something, to get back to the function, of course, we do the antiderivative, right? But just make sure that we have all the antiderivative. We have the constant c. So, for this initial value problem, we have a differential equation and the initial condition. So this is initial condition. And then we have a differential equation. Now, since the derivative is equal to this, to get back to the function, so I will write, if we have derivative is equal to x squared minus 2x, to undo the derivative sign, what we do is we find antiderivative. Just to make sure we have everything, we do the integral, indefinite integral. We have derivative, undo that, we have the integral, which is the set of all the antiderivative. I'm going to put x squared minus 2x in it. And of course I apply the power rule for this one. It should be easy. The power rule for x squared, x cubed over 3, right? Increase power by 1, divide by the same thing. Instead of write 2 plus 2, 2 plus 1, I just write 3. Integral of x, increase the power by 1, 1 plus 1 is 2, divide by 2. There's the minus 2 in front of it, then plus c. Alright. I recommend that we write any numbers at the bottom as the reciprocal. Any number at the bottom as reciprocal, multiply reciprocal. So that gives us 1/3 x cubed, 2 and times 1/2, that cancel out. That's 1 minus x squared plus c. Right. So this is the antiderivative. The indefinite integral of the function, meaning this is the family of all the antiderivative. The family of all the antiderivative. And finally, for the initial condition, for this we mean x equal to 1, the function of 1 is equal to 1/3. So the function is equal to 1/3 equal to, where we put 1 in for x, put 1 in for x, the whole function will equal to 1/3. And so we have 1 over 3 and that is 1 over 3 minus 1 plus c. Right, if we solve for c, we subtract 1/3 on both sides. Or we just cancel this on both sides. Minus c plus 1 minus 1 plus c equal to 0. So c is equal to 1. Right. So I have c equal to 1. And now since we know c is equal to 1, we can substitute in here. And so the function is, the answer is, so function will be equal to 1 over 3 x cubed minus x squared plus c, which is 1. Right. So this is the antiderivative satisfy the differential equation. and the initial condition. Of course, if we just find the indefinite integral, there will be a bunch of different functions, right? All of those functions. But only this function where c is equal to 1, only this function go through this point 1 and 1/3. When x equal to 1, the function is equal to 1/3. So there's a bunch of antiderivatives, but only one antiderivative satisfies this initial condition. And in this case, we just substitute the number and then to solve for that initial condition and to get the constant c. So initial variable problem, we find the antiderivative, all the antiderivative, and then we solve for that constant. And so we have this is called the particular solution to the initial variable problem. So the name for the solution in this form is called the general solution, and this is called particular solution. So integrate to undo the derivative and then solve for that constant. Right. Now, so once again, if we have derivative, integrate to get back to the function. Of course, when we do that, we have the constant c. Right, now, suppose an object moving along a line, a straight line with a known velocity v of t, then the position give us the initial variable problem. Same thing, the acceleration, then the velocity is equal to the initial variable problem is like this. So let's look at this example. Runner A at the point s0, s of 0 equal to 0, run with the velocity of 2t. Runner B with a head start at 8 and run with the velocity of 2, a constant 2. Find the position of the runner and determine who is ahead after 6 time unit, because we didn't specify the unit here, so we just say 6. Right, so there are two parts of the problem. When we go to section 5.3 and 5.5, we will do a lot more integral, but for now we just a very simple example. So first, runner A. We have the position, the velocity is equal to 2t. Velocity is the derivative of the position function, so I will write derivative is equal to 2t, where initially the position is at 0. Right. So I have the derivative. To undo it, to undo the derivative, I will integrate, right? So first, I'll say s of t will be just undo it and have the back to the position function, right? Velocity is equal to derivative of the position function, right? Apply the power rule for 2t. Power rule for t is t squared over 2, right? And then the 2, we don't apply another power rule for it because they multiply together. It is the constant multiplier, so we only apply the power rule for the power of t. No, unless you add the constant. Yeah, where's that? Yeah, if you add a constant to it, then we integrate that as well. But it have to be add a constant. We don't have that here. We have the constant multiplier. So we don't integrate 2. The 2 is the constant multiplier to it. Then plus c, right? So increase power by 1, divide by same thing. Now divide by any number, multiply reciprocal. 2 and 1/2 cancel out. That's t squared plus c. Right. Now we have the initial condition. So meaning that we let the function equal to 0 when t equal to 0. When t equal to 0, the function equal to 0. That's what it means. So because of that, c is 0. Which we can substitute into here. So the function is equal to t squared plus c, and c is 0. Right, that is runner A. Runner B, velocity is equal to a constant 2. Velocity is derivative of the position function. Now I use the capital S because this is capital V. So, and capital S and capital V. So derivative is equal to 2. And initially, it has 8. Once again, we undo the derivative by integrate. So, function integrate. Now just 2 is a constant. A constant rule says it's just that constant times the variable. That is the integral of a constant 2, and then the plus constant c. And that's it. Now initial condition. Meaning that we will make it equal to 8, where t is equal to 0. Right, that's simple enough. So 8 is equal to c, because 2 times 0 is 0. So that is c. We can substitute in here, and we have the initial, the particular solution, 2t plus a constant, which is 8. Now, so that's good and all, but the question is who is ahead after 6 with t equal to 6. So we do that. At t equal to 6, s of 6 is equal to 6 squared, which is 36. And over here, at t equal to 6, s of 6 is 2 times 6 plus 8. So that is 12 plus 8, 20. Of course, runner A will be ahead, even though B has a head start, but with a constant velocity. A, the constant, the velocity is not constant. The velocity is increasing. When t increasing, bigger the t, the bigger velocity. So because of the velocity is increasing, in the long run, runner A will get far ahead. If enough time, runner A will catch up runner B and will increase the distance between them. Right. So once again, velocity is the derivative of the position function. Same thing. Acceleration is the derivative of velocity. Right. Now we have an application problem here. Neglecting air resistance, the motion of object moving vertically near the Earth's surface is determined by the acceleration due to gravity, which is approximately 9.8 meter per second square. Of course, since the gravity pointing down, usually we can say it is negative 9.8 meter per second square. So in the English unit, that would be 32 feet per second square. And suppose a stone is thrown at t equal to 0 with the initial velocity of 40 meters per second from an edge of the cliff that is 100 meters above the river. Find the velocity of the object for t greater than 0. Right, let's just write velocity. What we have is acceleration is that. So we start with acceleration is the derivative of the velocity, right? So we start with acceleration is derivative of velocity, which is negative 9.8. Let's forget the unit. I mean, we write the unit later. And then we know that initially velocity will be at 40 meters per second. So at time t equal to 0, velocity at 0 is 40 meters per second. And this is upward, so we throw one up, the velocity is positive. Alright, so we have this initial value problem. So it's easy to get back to the function. By the way, in physics, instead of write the acceleration due to gravity, we can write g instead of a. But in here we just write acceleration in general, a. Right. Now we have derivative equal to that. To get back to the function, we integrate. Right, and that's just a constant. So integral of a constant is that constant times t, right? Then plus a constant c. Yeah, that's what we have. Now, initial value problem v of 0 is equal to 40. Meaning that we let velocity equal to 40, where we substitute in 0 for t. When t equal to 0, the function is equal to 40, and that cancels out, and we have c is equal to 40. We can substitute to that. So v of t is equal to negative 9.8 times t plus 40. Of course, if we want the unit, velocity is meter per second. Right, so we have the velocity. Next, I'll find the position of an object for t greater than or equal to 0. Now, the problem now becomes we have the velocity, right? Velocity, which is derivative of the position function. Now we do know the velocity or the derivative of the position function. Negative 9.8 t plus 40. And initially we throw it up at 100 meters above a river. So we should say s of 0 is equal to 100. Right, then we do solve this initial value problem. That should be easy. So derivative is that. To get back to the function, just integrate right. Now power rule for t and the constant t squared over 2, 40 times t, 40 times the constant times t, and then we have negative 9.8 times that, and then plus 40 times t, of course plus the constant c. Now divide by 2 is multiplied by reciprocal, plus 40 t plus c, so which is negative 9.8 times 2, so 9.8 divided by 2 is 4.9, negative 4.9 t squared plus 40t plus c. Now initial condition, s of 0 equal to 100. So meaning that the function value is equal to 100, where c equal to 0. Right, that's 0 cancel out, we just have c equal to 100. And we can substitute c equal to 100 into here. So finally we will have the function s of t equal to negative 4.9 t squared plus 40t plus 100. Of course, the unit here, the position is going to be meter. Right, so acceleration, integrate, give us velocity, integrate that, give us position. Next, find the maximum height of the object above the river. So now let's just write the position function. So position function, negative 4.9 t squared plus 40t plus 100. Velocity is negative 9.8 t plus 40. Acceleration is a constant, negative 9.8. So that's what we have. Right, now the maximum height. So which one do we use here? Now think about this. When we throw an object, it's going up and then it goes down. The gravity will pull it down always. Now when it reaches the apex or the vertex of the problem at the highest point, it is neither go up or down. So you could say that it is stationary at that moment where it is at the apex. If it is stationary at that instant, if it's not moving, meaning the velocity will be at 0 when at the highest point. So at the highest point, it is neither go up or down, meaning it is stationary at that moment, meaning the velocity is equal to 0. So we said at the highest point, velocity is equal to 0. So we have negative 9.8 t plus 40 equal to 0. So we solve for t equal to negative 40 over negative 9.8. Divided by 9.8. Yeah, that's about that. Just say 4.1 second. So after 4.1 second, the object will reach the highest point. And if we want to find the position of that, just put 1 into the position, 4.1 into the position function. So negative 4.9 times 4.1 square plus 40 times 4.1 plus 100. Right. Since I have that number, right, I can just store that into x. And then we have negative 4.9 x squared plus 40x plus 100. And I have 181.6. Notice that this is just a round number. In the calculator, I prefer to use all of the decimal places, so the answer will be more accurate. And the unit, of course, will be meter. So that is where the object is at the highest point. Next, at what speed does the object strike the river? Right. So when the object strike the river, what's so special about that? Of course, the gravity pulling down, so the constant acceleration is always a constant, negative 9.8. Velocity will change, position will change, but when it strikes the river, the position is equal to 0. Right? Because we assume that the distance is above the river. Yeah. So in that case, I will let this function equal to 0. So we have negative 4.9 t squared plus 40 t plus 100 equal to 0. Of course, we just use quadratic formula here because the 4.9, I don't want to factor it. And it's not going to be any nice and even either. Right, quadratic formula. Right. Negative b plus or minus b squared minus 4 a c over 2 a. Right, we'll enter the whole thing here. This fraction, negative 40, head to the minus first, square root 40 squared minus 4 times negative 4.9 times 100 over 2 times negative 4.9, right? And we do that, we have There's something off here. Yeah. Right. So at 10.16. Right, what happened if we have a plus? Right, we have -2. Of course, time cannot be negative, so t is going to be 10.16. So when we throw the stone up after about 10.16 seconds, the object will strike the river when the position equal to 0. So at t equal to 10.16, they said what is the speed or the velocity? So notice that I will take, that's 17 actually. It doesn't matter, I'll take the whole number, store into x. Then I can evaluate. Velocity is this, -9.8 x plus 40, which is -59.67. If we want to unit meter per second, of course it should be negative, right? Simply because it's going down. But if we want the speed, we just take the magnitude or the absolute value of this. So that will be just 59.67. The unit is meter per second. So that is the speed. Right. So that is the application. Once again, acceleration is the antiderivative of velocity. Velocity is antiderivative of, I'm sorry, I got said that backward. Acceleration is derivative of velocity. Velocity is derivative of position function. Now, if we are given, of course, the gravity or acceleration due to gravity usually is -9.8. I said usually, meaning very close to the sea level. The gravity is -9.8. The further away from the center of the Earth, the further away from the center of the Earth, the less gravity we have. So, but when we have acceleration integrate, we have velocity antiderivative, get us velocity, and do that again, get us the position function. So integrate. That's what we have here. Right. I'll go back to do more sample. Determine the indefinite integral for this one. So we have power rule here, because here we do not have any trigonometric function. X squared at the bottom, we can write that as x to the -2 Now apply the power rule. This time I will do slowly. I increase the power by 1, divide by the same thing. Now for x, by default, to the first power, increase the power by 1, divide by the same thing. And for constant 2, and x to it. So we multiply 2 plus a constant c. So negative 2 plus 1 is negative 1. Negative 2 plus 1 is negative 1. X squared over 2 plus 2x plus c. Right. Now divide by numbers, multiply reciprocal. Divide by negative 1, it's just like multiply by negative 1, so actually, yeah. Or just multiply by negative 1, it's not wrong. Divide by 2 is multiply by 1/2. I recommend to do it like this. So that gives us negative 3 x to negative 1 plus 3/2 x squared plus 2x plus c. So that's what we have. Right? Yeah. So in this section, the rules we have up to this point for the integral, just the power rule and trigonometric rule. Later on we will have a few more. But that's all we have this section. Right, one more. Let's solve the initial value problem where we have a bunch of derivatives. So just do it one by one. Fourth derivative is that. I mean the third derivative. If the third derivative is that, to undo it, undo one of them. So from the third derivative to get back to that, we integrate. Right? Third derivative, go to second derivative, integrate. Power rule here. X to the first power by default, integrate, give us x squared over 2 plus the constant c. Divide by 2, multiply reciprocal, 1/2. Four times 1/2 is 2. Right. Now the initial condition, the first initial condition, f prime of 0 equal to 0. Double prime of 0 equal to 0, meaning that this is equal to 0, where we substitute in 0 for x. So here c is equal to 0, right? Because 0 cancel out. Right. Substitute c equal to 0 into here. We have second derivative is equal to 2x squared. Now, if we want to get rid of one of the derivative, we integrate again. We still have one of the derivative. So that double integral, double derivative, double prime, integrate, get us back to 1, the first derivative. Again, power rule. Increase the power by 1, divide by the same thing. That is the power rule. Any antiderivative plus the constant c. Right? Divide by 3, multiply reciprocal. So give us 2 over 3 x cubed plus c. Now we have another initial condition. Derivative is equal to 1. Meaning that we will let this equal to 1. we put 0 in for x. Right. So that cancel out and c equal to 1. Substitute that in here. So we have the derivative is equal to 2 over 3 x cubed plus 1. Right? And we'll do one more step to undo the derivative. To get back to the function, we integrate. And once again, we use the power rule. X cubed will be x to the 4 over 4. X to the 4 over 4 2/3 times it. Integral of the constant 1 will be just 1 times x plus the constant c now divide by 4, multiply reciprocal x to the 4th plus x plus c, and 2/3 times 1/4 is 2 over 12. 2 and 4 cancel out, 1 and 2, so it would be 1 over 6. Plus x plus c, and we have the final last initial condition, f of 0 equal to 3, meaning that it is equal to 3 when we put 0 in for x. Of course, when we do that, 0s and 0, so c is equal to 3. And we substitute that, c equal to 3 into here. Bottom line is the equation run out of space, but will be that plus c is 3. So we have f of x equal to 1 over 6 x to the 4th plus x, c is 3. Of course, if we want to, we can check by taking derivative of it. So we have the function is that 1 over 6 x to the 4th plus x plus 3. Right? Now, we will take derivative. Be 1 over 6 derivative of x to the 4th for x cubed. Derivative of x is 1. Derivative of 3 is the constant. Derivative of constant is 0. 4 over 6 is 2/3. Now take derivative one more time, give us the second derivative. 2/3 times 3x squared. Derivative of 1 is a constant, 0. 3 and 3 cancel out to x squared. And then take derivative one more time. We have third derivative equal to 4x. And of course that is consistent to what we have here. Yeah. Right. So of course in this section we study about antiderivative. Antiderivative is just one function. So when we plus the constant to it, we have all of the antiderivative, and all of the antiderivative is called the indefinite integral. And that's what we actually learn in this section. And always, thank you for watching, and see you in another video in Calculus 1.